Okay, welcome back to another recorded lecture here for chapter 5. This is going to hopefully complete chapter 5 and apparently our recorded lecture series. So, when we last left, and again, this will be picking up from the last recorded uh, lecture there on chapter 5, which I think is labeled part 3. So, I guess this would be part 4. Uh, we left off talking about stoichiometry, and stoichiometry is where we kind of combine the two aspects of what we've been talking about, which is we combine moles and balanced equations. And what we can do with those is we could do calculations that are based off of a balanced equation to figure out certain aspects of that equation, like how much products we would make. We could also figure out if we know how much products we made, we could figure out how much reactants we started with. So we could do a lot of calculations from the balance equation and really just one piece of information um, from that equation. And in a basic stoichiometry problem, as we talked about last time, there's really kind of four basic steps. The first step is you do need a balanced equation. And none of this works right if you don't have a balanced equation. Next, what you need is you need to convert whatever they give you into moles. And usually, a lot of times, you're given grams at this step. And again, we can go to moles by using the periodic table and the molar mass. Yeah. So the molar mass is really our conversion factor there to do that from the periodic table. And step number 3 in a sort of a basic stoichiometry problem is really the big stoichiometry step, the thing that people always sort of worry about or maybe get wrong. And this is you go to the balanced equation and you find the mole to mole relationship of what you're interested in. So, for example, if I in the equation above was given information about CO. So I was given say how many CO I have, but CO I want all CO. That is the two things we would go to the equation and find the mole relationship from. And remember that the mole to mole relationship is nothing more than the actual coefficients that we see in the balanced equation, which is why it's so important that the equations are balanced for these things to work out correctly. We again could say that if we look at this equation, we could find a lot of what is referred to as stoichiometrically equivalents, are things that are equal to each other. We could say that for every 2 moles of CO, we would also have to put in there 1 mole of O2. And this is all based upon the coefficient, no calculation there, just actually what the coefficient is in the balanced equation. And that would represent the moles of each of those things. We could also say for every 2 moles of CO we throw in there, we get 2 moles of CO2 out. We also say for every 1 mole of O2 that we put in there, we could get 2 moles of CO2 out. So as we finished up last time, I think talking about this, these are equalities. These are stoichiometrically equal to each other. They are equal to each other in terms of like proportion wise. Like you need to throw in 2 moles of CO with 1 mole of O2 to get this reaction. They clearly in terms of 2 we talked about last time. But really think about these and just like this equation. So if I took this of CO, middle one, we lastly, you can actually get from this one equation. And that's really what stoichiometry is. Stoichiometry is really nothing more than a conversion factor. And the difference is in a normal conversion factor, like if you wanted to know how many inches were in a foot, how many inches in a centimeter, you would go to a table and sort of find that information. Where we find the conversion factors in stoichiometry from is the balance equation. And really the goal is, like in this little example here, The only information I have is about CO, but I really need some way to relate it to CO2. And that's where the stoichiometry part would come into play. So for that example, we would want to use this relationship, which again gives us these two conversion factors here. And much like a normal conversion factor, you would only use one of them. So you could do a dimensional analysis where you take the moles of CO and then use that stoichiometry to go from moles of CO, which we would want to use the one on the right so that everything cancels, to moles of CO2 in this case. The moles of CO would cancel. That would leave us with moles of CO2. So really that's what stoichiometry is. It's using the equation really as a conversion factor where we're able to say that the coefficients that we find in the balance equation represents the moles of each of those guys. And again, that mole to mole relationship is what allows us to figure out, go from one thing in the equation to another. Now, when we do this sort of mole to mole relationship, we can go from the left-hand side of the arrow to the right-hand side of the arrow in terms of relationships. We could go from the right-hand side of the arrow to the left-hand side of the arrow in terms of mole to mole relationship. We actually don't even need the cross over the arrow. Like here in this example, we have two things on the reactant side. We could find the relationship, mole to mole relationship between these two guys. If we had an extra product, we could also do that on the product side as well. So once we get to the moles of really what we're interested in here, we would do step number 4, which is convert those moles, because you will always be in moles at that point, into some other unit. And if the answer was going to be in moles, you would actually stop your calculation. But a lot of times you do have to do that step, and a lot of times you may go from moles back to grams. And again, to do that, we would use the molar mass to do that, again, for the periodic table. But it doesn't necessarily always have to be grams. You could have something like maybe they want pounds or some other type of unit. So when you get to step number 4, you may have to do it, and you may have to do multiple conversions at that point, or you may not even have to do it if they want it in moles. All right, so let's put this into practice here and take a look at an actual problem here and sort of follow through those steps. So here we're going to take lithium metal, reacts with water to form hydrogen gas and lithium hydroxide. We want to know how many moles of hydrogen gas can be formed from the complete reaction of 5.32 moles of lithium with water. So again, following our 4 basic steps for a stoichiometry problem, step number 1 is we need a balanced equation. Now, in this particular problem, they gave us everything in words, so we want to make sure that we turn these words into the correct formulas first. So lithium metal is lithium that does not have a charge. It's just solid by itself. Reacts with water, which is H2O. And that forms lithium hydroxide, with its LiOH, Li plus 1 in that case, OH minus is minus 1, obviously. And that produces also hydrogen gas. So the first thing we want to do is get all the correct formulas down. We don't want to worry about balancing or anything like that, but we do want to make sure that our equation is balanced. And when we look at it here, it is not balanced. So to balance this equation, I think, I'm just going to give it a try. We need a 2 there, we need a 2 there, and we need a 2 there, and I think that's all the 2's we need. So we have 2 lithiums on both sides. We have 4 hydrogens on both sides, 2 here and 2 at the end. We have 2 oxygens on both sides, so we have a balanced equation. So check for the first part here. Step number 2 is to take whatever they gave you and convert it into moles. So in this problem, they gave us that we are starting with 5.32 moles of lithium. And remember, we want to go from moles of lithium, and eventually what we're trying to find is how many moles of hydrogen gas. Now, this brings up a very important point when you're doing stoichiometry problems, and sometimes people do some weird things like undo things. You never want to undo things. So when we talk about these 4 steps, if something is already done for you, don't undo it and redo it. So in this particular case, it's already done for us. It's already in moles, which means we don't have to do that conversion. So like I said before, don't do anything like undo it and then redo it. So then what we do is if something is done for us, we just go to the next step. And the next step in that process is to go to the balanced equation and spell balance right. Try that again. Balanced equation. And we want to find the 2 things we're interested in. One thing that you're always going to be interested in is essentially what they gave you. So obviously we're interested in the lithium. The other thing that we're interested in is what we're trying to find, which is the hydrogen gas. So we'd be interested in that. And this is where we could do our stoichiometry. We see from the equation, again, the coefficient, that there are 2 moles of lithium gives us 1 mole of H2. And in this case, from that equality, we could write 2 conversion factors. We could say 2 moles of lithium on top over 1 mole of H2 on the bottom. Or we could say 1 mole of H2 on top gives us 2 moles of lithium on the bottom. So we're going to pick the one that's going to help us get to where we're trying to get to. So right now we get to lithium, and we want to get rid of lithium and end up, which means this conversion factor here is the correct one. Lithium, moles of lithium need to go on the bottom, and on top would be the moles of hydrogen. This is the big stoichiometry part. This is the part using that's going to allow us to go from moles of lithium, which is ultimately not what we're looking for, to moles of hydrogen, which is what we're looking for. And the 5.32 divided by 2 gets us 2.66 moles of hydrogen gas. And that would complete step number 3. Now remember, step number 4 is to convert the moles, because you will always be in moles at this step, to some other unit. Now, this is also something we need to think about. We need to think about the question. And the question said, we want to know how many moles of H2. So in this particular problem, we actually do not need to do step number 4, because step number 4 is not necessary, because this is actually the amount of moles that we would produce in this case. Now, what that number represents, and whenever you figure out from an equation using stoichiometry how much product you would make, this number represents what is known as the theoretical yield. And the theoretical yield is basically the maximum amount of product that you would make. And really what these numbers mean is, if you take this equation that we just did and you put in there 5.32 moles of lithium, you should get out, if everything went perfect, if you didn't spill anything, there was no side reactions, you technically should get out 2.66 moles of H2. And that's what, again, what is sometimes referred to as a theoretical yield. Although we did not need to do step number 4 in this problem, we could do step number 4 by, if we were looking for grams, use the molar mass from the periodic table to do that. So all these stoichiometry problems, especially these basic stoichiometry problems, they're all essentially the same 4 steps along the way. So let's continue on and take a look at another example here. And this is actually the same question. Let's get to this question, which is different. This question here is using the same reaction. So we're doing the exact same reaction. The difference here, though, is we are starting with 81.75 grams of lithium. And what we're trying to find in this case is how many grams of hydrogen we produce. So because it's the same reaction as what we did before, we already have the balanced equation. So that's step number 1, which is already done. Step number 2 is the same. We want to take whatever they gave us and convert it into moles. So the question is, do we have to do that in this particular case? And the answer is yes, because what they gave us was not the moles of lithium in this case, but they gave us the grams. So we need to go to the periodic table and find the molar mass of lithium, which again, when you go to the periodic table, that is the number that you see on the bottom, which in the case of lithium, 6.941. So what that means is that molar mass of lithium, you could use the molar mass like a conversion factor. If we do that calculation there, we get 81.75 divided by 6.941 gives us 11.78. I'll take it to a couple of digits at this point. 11.78 moles of lithium. So that is step number 2. Step number 3, again, is the stoichiometry part. We're going to go to the balanced equation. And find the mole to mole relationship of the 2 things we're interested in. So again, the 2 things we're interested in is, one thing is what they gave us. So in this case, just like in the last one, they gave us lithium. And just like in the last one, we're interested in the H2. So we get the same equality that 2 moles of lithium will give us 1 mole of H2. And that also will give us the same 2 conversion factors that we technically could use. 2 moles of lithium over 1 mole of H2 are 1 mole of H2 over 2 moles of lithium. So taking our answer from step number 2, we are in moles of lithium, which we want to get rid of, because ultimately we're interested in that H2. So we're going to use the coefficients from the balanced equation, which is the stoichiometry, to do that. Again, we're going to use the conversion factor on the right because that has the lithium on the bottom. And we have our moles of hydrogen on top, which is what we're looking for. Again, the moles of lithium are going to cancel. We're going to take 11.78 divided by 2, gets us 5.89 moles of H2. This technically would be your theoretical yield. In moles. But this problem is different than the previous one because we actually don't want to stop this time at moles. What we're looking for is grams. So in this particular problem, we do have to do step number 4, which is to convert our moles into grams. Now, the important part to remember is at this point, we are no longer dealing with lithium. We have now used stoichiometry to convert to H2. So when we go to convert these moles into grams, we actually now need the molar mass of H2, which again could also be found on the periodic table. That is 2 times 1.008 grams per mole, which is what you find on the periodic table underneath hydrogen. And that gives us a molar mass for H2 of 2.016 grams per mole. And again, we're going to use this as a conversion factor to get rid of our moles. In this case, we want the moles on the bottom. So 2.016 grams of H2 per mole of H2. The moles will cancel each other out. And if we multiply that by 5.89, we will get 11.9 grams of H2. And this would be our answer in this case. This also would be the theoretical yield, just in a different unit. In grams. So hopefully you can see that this is the same 4 steps that we did previously, but in this case, we actually did have to do all of the 4 steps here. So we have our balance equation. We had to convert grams to moles using the periodic table. We used our mole to mole relationship, which came from the balanced equation. And then once we had moles, we actually again needed the molar mass from the periodic table to take those moles back into grams. So what this number means is in this same reaction, if you dumped in there 81.75 grams of lithium, everything happened 100% perfect, no side reactions, nothing spilled. You, in theory, which is why it's called the theoretical yield, you should get out 11.9 grams of H2. And let us continue on looking as maybe another example we might have here. That's the same one. So let's take a look at, this one. And again here, we have an equation. We're given information about one thing in the equation. And in this case, we want to know the mass of CO2 that's going to be produced. So again here, this is going to be a stoichiometry problem. So whenever you could recognize it as a stoichiometry problem, you want to get in your head sort of the steps that you need to follow, to complete it. So in this case, the first thing we want to do is have a balanced equation. So that's right here. And I see coefficients. So probably unless somebody's trying to, mess you up on purpose, if you see coefficients, is probably balance the equation. If you don't see any coefficients, you should definitely take a moment and double check that it's balanced. But probably 9 times out of 10, if you do see those coefficients, it's probably going to be balanced. The next thing we want to do is take whatever they gave us and convert to moles. So in this case, the only information that is given to us is 765 grams of C6H12O6. And ultimately, what we want to do is go from grams of C6H12O6, and we want to eventually end up with grams of CO2. So as we talked about before, to go from grams to moles, we need to go to the periodic table, and we need to get the molar mass of our C6H12O6. We're essentially just going to add up all the parts there. So there are 6 carbons, each from the periodic table 12.01, plus 12 hydrogens, each from the periodic table 1.008, plus 6 oxygens, each from the periodic table 16 grams per mole. And we just want to add up all those numbers, and that will give us the molar mass of this compound here. So that's 6 times 12.01 plus 12 times 1.008 plus 6 times 16 gets us 180.2 grams per mole. And again, that is the molar mass. That is essentially what we could use as a conversion factor. So I'm just going to rewrite it down here since I kind of got in the way up there. So we're going to take the molar mass from the periodic table that we just calculated. We're going to put the grams on the bottom so that they cancel. Moles on top. Again, the grams will cancel. And if you get a number at this point, which, by the way, you don't have to necessarily get a number at this point. You could do all this in sort of one big calculation if you liked. If you do get an answer like I'm doing, you probably don't want to round too much until the end. 4.245 moles of C6H12O6. Now, in this case, we now want to do step number 3, which is, again, the stoichiometry part. We want to go to the balanced equation. And we want to find the 2 things we're interested in. And in this case, we're interested in C6H12O6 and CO2. And from the equation, we could see the relationship, which again is a stoichiometry relationship. And again, it's just the coefficients. We see that for every 1 mole of this guy, we actually will get 6 moles of this guy. So for every 1 mole of C6H12O6, which is the coefficient, we get 6 moles of CO2. That again is going to allow us to write 2 conversion factors, 1 mole of C6H12O6 over 6 moles of CO2 are the opposite. 6 moles of CO2 gives us 1 mole of C6H12O6. So we want to choose the one that's going to help us get to where we need. And again, just so happens to be it's on the right-hand side here. So we're going to take our 4.245 moles from the previous step. We're going to do the stoichiometry part, which again comes from the balanced equation. We're going to put the moles of C6H12O6 on the bottom, the 6 moles of CO2 on top. That is the big conversion to go from one thing in the equation to something else. So timesing that by 6 gets us 25.47 moles of CO2, which in this case, again, would be our theoretical yield. In moles. And by the way, the theoretical yield can only be on something that's a product. So if you yield something, it's always got to be something on the product side. So you can't have a theoretical yield if you went the other way and made a reactant. It could only be the product side. But this is very close to what we want. We got moles of CO2, but we actually want grams. So in this case, we again do have to do step number 4. So if we do step number 4 here, we're going to convert our moles into grams. And in this case, again, we want to remember that we have now used stoichiometry to get to CO2. So we do not want to use the same molar mass that we used earlier because that was for C6H12O6. So we do need to go to the periodic table and get that molar mass of CO2. And that is 12.01 grams per mole for the carbon, plus 2 times 16 grams per mole for the oxygen. And that will get you 4401 grams per mole as the molar mass for our CO2. And that's what we need for our very last step here, 25.47 moles of CO2, which is what we got in step number 3. We will then use the molar mass with the grams on top so that we end up with grams, moles on the bottom so that the moles will cancel out, and we will end up with 1121, we'll call it. And we got 1121 grams of CO2. So now let's talk about significant figures. The only number in this entire problem was pretty much this one. And this number has 3 significant figures, which means when it's said and done, this number here should technically end up at 1120 grams of CO2, which would be our 3 significant figures. You could also, again, write it as 1.12 times 10 to the 3 grams and use scientific notation. So 1120 grams is our theoretical yield of CO2, obviously in grams, yeah? And this means the same thing is if you put in there 765 grams of the C6H12O6, everything went perfect in this reaction, you should get 1120 grams of CO2 out. Again, you should hopefully be able to see it is the same 4 steps. Although in these couple examples or 3 examples, we went from the left-hand side of the arrow to the right-hand side of the arrow. Again, you could do these same 4 steps with somebody that's on the same side of the arrow. Like, for example, between the C6H12O6 and the O2. You could also do it on the right-hand side of the arrow with those guys, between the CO2 and H2. You don't necessarily have to cross over from, left-hand side to right-hand side to left-hand side. You could do this sort of stoichiometry calculations for really anybody in that equation. All right. So again, just to sort of demonstrate that really quick, let me just rewrite this here. So we had C6H12O6 plus a little bit of O2, CO2 plus some water, and 666 there. So let's just say, for example, you were given that you produced, we'll just start with moles to make it a little bit easier. You produced 32 moles of CO2, and you want to know how many moles of H2O would you make, and also how many, if I spell many right, there we go, moles of O2 did you start with? So in this particular problem, we're actually starting with over here on this side. And you would do the same steps. So the first step is we still have our balance equation. The next step is we want to convert to moles, which it actually is done for us, right? So we actually are starting with 32 moles of CO2. So we don't have to do that in this case. The next step would be to find what we're interested in. So we're actually interested in a couple of things here. So we'll start with one at a time. So step number 3, we're interested in going from CO2 and actually staying on the same side to H2O. And from the equation, we can see that for every 6 moles of CO2, you also get out 6 moles of H2O, which again will give us our 2 conversion factors that we could do. Or we could have 6 moles of H2O over 6 moles of CO2. And if we were to do that problem, we would take our 32 moles of CO2. We would use the conversion factor that's going to help us, which is this guy. Again, won't always be the one on the right. To 6 moles of H2O. Again, from the equation, that's the stoichiometry. And in this case, we would actually end up with 32 moles of CO2 as well. And in this case, this would be the answer. We don't have to do step number 4, not needed here, because it wanted moles. If it wanted grams, we would use the molar mass like we used in the previous problems to do that, if it did want grams, but it didn't ask for it in that case. So as you can see there, we could do the relationship without even crossing the arrow. We could stay on the same side. Or we could even start on the right-hand side and end up to the left-hand side. So that's the case for the second part. In the second part, we want to know how many moles of O2. So in this case, if we know we are starting with CO2 and we want to get to O2 as well. And from that relationship, we see for every 6 moles of O2, we get 6 moles of CO2, which will give us 2 conversion factors as well. 6 moles of O2 over 6 moles of CO2 are 6 moles of CO2 over 6 moles of O2. So again, we would start with what we were starting with, which was our 32 moles of CO2. And again, here we want to get rid of CO2. So we want the CO2 on the bottom, which in this case is the one on the left. That's something different. That's good. The CO2, 6 moles of O2. And again, the moles of CO2 will cancel in this case, and that will get us 32 moles of O2. And same deal here, since we were looking for moles, we don't have to do step number 4. It's not needed. But if you did need to go to grams, again, you would use your molar mass to do so. So just to clarify, spit that word out. This one, since it also is a product, would also be a theoretical yield because it is a product. While this one down here would not be a theoretical yield. It's really just how much OT you would start with. And again, you could convert it to grams. So again, sometimes people think you always have to go left to right on the stoichiometry and the arrow, but you can go any way. You could go from products to reactants in terms of the calculation. You can stay on the reactant side. You can stay on the product side, but you have whatever options there is. What we have talked about up until this point is what is known as really basic stoichiometry problems. We're going to talk about a little bit more complicated stoichiometry problems. It is still going to be the basic steps here, but there's a couple of extra things that you need to do to sort of solve these type of problems. So let's take a look at these. And these involve limiting reagents. And limiting reagents is pretty much what the name sounds like. Whenever you do an actual reaction, And you have your reactants. So you have A plus B, that goes to C plus D. When you look at your reactants, which is on this side, which is your starting material, sometimes called reagents as well, because those are things you're mixing. There's always one of these reactants that gets completely used up first. And the reactant that gets used up first is what is known as the limiting reagent. So that's your limiting reagent. Sometimes people will call it limiting reactant, same deal, but it's your limiting reagent. And there will be one reagent that you have plenty of. And it will actually still be there after the reaction is over. And that is what is known as your excess reagent. So your limiting reagent is the one that gets used up first in the reaction. The excess reagent is the one that you got plenty of. You have so much of it that when the reaction is over, and by the way, the reaction is over when the limiting reagent is used up, that you actually still have some of that excess reagent left over. And again, that's what that says there, our excess reagent. It's our leftover amount. So the important part is when you do a reaction, the important one out of the excess reagent and the limiting reagent is the limiting reagent. The limiting reagent is important because it will determine how much product you will make. So for example, if I have this reaction where I take A plus B to make A and B together, that implies that for every product that I make, I need to put A and B together. Now, if A was my limiting reagent, LR, and B was my excess reagent, as soon as I run out of A, there is no possible way to continue to make product, because in order to make this product, you need both of those things. You need A and B coming together. So between the limiting reagent and the excess reagent, we always use the limiting reagent to determine our yield. And a lot of times that's your theoretical yield that we've been talking about. Now, you may say to yourself, we figured out our theoretical yield in the earlier sort of stoichiometry problems that we did. And you're right, we did. And what makes those problems different than what we're going to see in just a second is in those problems, they only gave you information about one reactant, for example. And when you're given information about one reactant, that implies that that reactant is the limiting reagent, and it is the one that's going to determine how much product you make. And that also brings up the point of how you know it's a limiting reagent problem. The big way that you know it's a limiting reagent problem is when you are given information in the problem. You have enough information to calculate the moles of each reactant, not just one of the guys on the left-hand side, but you have enough information given to you to calculate the starting moles of each of the reactants. And that is definitely how you know you have some type of limiting reagent problem. The good news is it's kind of the same 4 steps still. You're still going to balance your equation. You're still going to convert to moles just like we did before. You're still going to go to the balanced equation and find the mole to mole relationship. And you're still at the end probably going to convert those moles to some other units. There is just one additional sort of calculation you have to do usually, and it happens right about there. you need to be able to determine which reactant or reagent is the limiting. So there's this one extra little sort of calculation that you have to do to figure out which one's the limiting reagent. Once you do, then you would continue on with step number 3 and step number 4, using the limiting reagent. So it's important that you use the limiting reagent for that one. So let's take a look here. So here's an example. If we want to make, we have guy workout buddies, guys on that side, girl workout buddies on that side, and we got one guy and one girl to make workout buddies. We could see from this that our limiting reagent is going to actually be the guys here. We're going to run out of guys first, while we have plenty of the girl workout people, and that would be our excess reagent. So again, since we need one of each of those, at some point, once we run out of guys, we will have plenty of the girls left. And we could even figure out something like is very commonly asked, how much of that excess will be left over? So very simple. In order to make workout buddies, we need one girl and one guy. We need one girl and one guy. We need one girl and one guy. And not change the page there. Try that again. And one guy. And at this point, we have now used up all of our limiting reagent. And we can see that what we have left over in terms of the excess is we have 1 in this case and 2 in this case. So we do left over our excess reagent. And that also is another thing that you're commonly sort of asked to do, is to figure out how much of that excess reagent is left over. All right, now we got pictures. Let's take a look at an actual sort of situation and try to figure out how we could figure out which one is the limiting reagent and which one is the excess reagent. So let's take a look at this equation that we have up on top, and let's assume that we are starting with 4 moles of S, and we're also starting with 20 moles of F2. Now, we have a balanced equation. We have the starting amount of both reactants given to us. And that right there should tell you this is a limiting reagent problem, which means you do need to do something to figure out which one's the limiting reagent. Now, the second thing you would want to do, obviously, like normal, is convert what they gave you into moles. But in this particular case, it was already converted into moles, so we did not have to do that. Now, there's many different ways that you could solve a limiting reagent problem. So I'm just going to kind of show you one approach, and it may be slightly different than what's in the book, or maybe you see somewhere else. But truthfully, there's like 3 or 4 different ways you can sort of solve these problems. So we're just going to go with this approach here. So everybody's clear, once you do step number 2, what that will give you is the starting amounts of both of your reactants, which in this particular example is 4 moles of S, and we're starting with 20 moles of F2. Now, in order to figure out which one of these guys, the S or the F2, is the limiting reagent, what we want to do is do a very simple calculation involving stoichiometry, where we basically say, this is basically what we're saying, if we want to use up all of my, and I'm just going to pick the sulfur in this case, how much F2 do I need? So this little calculation that we're going to do, which tells us if I want to use up all my S, how much F2 do I need to put in there, is going to allow us to figure out which one's the limiting reagent. So what we would do is we would start with the 4 moles of S, And we do need to go to the equation in this case and find the relationship between S and F. And we see, like it says up here, for every 1 mole of S, we also need to put in there 3 moles of F2. So we're going to use that. And again, those two conversion factors that you could get from this. So our 3 moles of F2 over 1 mole of sulfur. Now we want to get rid of the sulfur in this calculation. So we're going to put 1 mole of sulfur on the bottom and 3 moles of F2 on top. The moles of sulfur will cancel, and that will tell us we need 12 moles of F2 is needed. So what that calculation says is I need to put in there 12 moles of F2 if I want to use up 100% of all the sulfur. Now, this is the part where you're going to do a comparison, and you're going to compare how many moles, in this case, of F2 you started with, which was given to us in the problem here, which was 20 moles. This calculation tells you the moles of F2 that is needed to use up all of that sulfur, which is 12 moles. And you want to compare these two numbers and see if you have enough. And you should be able to see that if you only need 12 and you started with 20, you have enough. And what that calculation tells you when you figure out you have enough is it tells you that the F2 in this case is going to be our excess reagent. And the nice thing about figuring out which one's your excess reagent or which one is your limiting reagent is, by default, the other guy has to be your limiting reagent. So this calculation right here was enough, this one right here, was enough to say, if I want to use up all of the sulfur, this is how much F2 that I need. And based on this calculation, I can see that we have enough. And what that would mean is if I wanted to figure out how many moles of the SF6 I would make, which is our product and also our yield, right? We want to make sure that we use the limiting reagent to do that. So once we've done this calculation, you may not need to use this number or this calculation for anything other than what we just did, which was figuring out which one's the limiting reagent. Now, to do the actual calculation, we would go back to the 4 moles of S, which is our starting amount. And now what we would need is the relationship between S and the product, which is SF6. And we see that 1 mole of S gets us 1 mole of SF6. And that means that we would do a stoichiometry little step here and do our 1 mole of S gives us 1 mole of SF6. And that would say we would produce 4 moles of SF6 in this case, which would be our theoretical yield in moles. And if we want grams, if we want to and basically figure out how many grams to produce. But it's not saying for that, it's a little step between the reagent, and then you can continue on to step number 4. Now, in this particular case, I chose how much Q I would need to use up all of my S. It doesn't matter which one you choose. You could choose the F2 and do the opposite calculation. So that's what I'm going to do on the next page just to show you it doesn't make a difference. So we have the equation perfect. We had 4 moles of S we started with. We had 20 moles of F2 that we started with. Again, this is our starting amount. And if you remember, we figured out the limiting reagent by figuring out how much F2 we needed. We could do the opposite calculation here. If we want to know how many moles of S is needed, to use up all of the F2, we would do a similar calculation to what we did on the other one. We would start with our 20 moles of F2. It would be the same relationship that we used on the previous slide, where from the equation there are 3 moles of F2, which means if we take the 20 moles and divide it by 3, we get 6.67 moles of sulfur is needed. So we use this to figure out, in this case, by choosing the other reactant, that we would need 6.67 moles of sulfur. If you remember, our starting amount of sulfur was only 4 moles. So when we compare these numbers, we see we do not have enough. And what this will tell us is exactly what it told us in the previous calculation, that since we do not have enough, since that's how many moles of S we started with, that the S here again is our limiting reagent, and the F2 would be our excess reagent. So what this calculation demonstrates is, in order to determine which one is the limiting reagent, I'll go back a page here. You can pick either one of the reactants and do a similar calculation. And you don't have to do both, by the way. Not in all cases, you don't have to do both. You could just do one of the calculations. So what I mean by that is, you could either do this calculation and then continue on to this final step. Or if you didn't choose that one, you could do this calculation and you would continue on to that same final step, again using the 4 moles, because we would find the same thing out, that it is the 4 moles of sulfur that's our limiting reagent. And again, just like what we did on the previous page, we would use the limiting reagent and the starting amount to figure out how much product, just like we did there. And you can see you get the same answer in terms of our theoretical yield. So the important part is, once you figure it out, the limiting reagent, that you use the limiting reagent to figure out how much product you make. Again, doesn't matter which reactant you choose to do the calculation about using up one versus the other. They both will give you the same answer, not the same answer in terms of numbers, but the same answer in terms of which one's the limiting reagent and which one's the excess reagent. All right, so let's take a look at this one here and figure out, what is going on here. So Fe, so we got 683 grams of iron, 934 grams of sulfur. And we have our equation here, Fe and S. Okay, the first thing that we want to figure out eventually, how many grams of our product here. So the first thing we want to do is, we know it's a limiting reagent problem because they gave us information about both of these guys. We have the grams of both of them, which is going to allow us to calculate the moles of each of them. So that automatically tells us this is a limiting reagent problem. That means that as we go through our 4 basic steps, right around here in between step 2 and step 3, we need to do that little calculation like we just saw to figure out which one is the limiting reagent. First things first, we have an equation. It is balanced, so we're good. The next thing is we want to convert into moles. So down to value, 55 grams per mole of sulfur, and variable is where we get each of those numbers. And 6.83 divided by 5585 gets us 0.122 moles of iron, and 9.34 divided by 32.07 gets us 0.291 moles of sulfur. Now, just so we're clear, what we've done is the second step, and what these numbers represent, which you do need to keep in mind as you're going through this type of problem, is these are your starting amounts. So this is the starting amounts of each reactant. Now, because this is a limiting reagent problem, we do need to do that calculation. So again, here you could choose either one of these. It doesn't matter which one you choose. So I'm going to choose the iron, and I want to figure out if I want to use up all of my iron, how much sulfur is needed. So again, I chose to use up all of the iron. You could do the opposite calculation where you try to use up all the sulfur and figure out how much iron you need. So we're going to take our starting amount of iron, which is 0.122 moles of iron. And now, because we are interested in how much of the other reactant, we want the relationship between these two, which seems pretty easy. It's a 1 mole of iron gets us 1 mole of sulfur, which I think I could do that. So that's going to be 0.122 moles of sulfur is needed. So this is the part where you can figure out which one's the limiting and which one's the excess reagent by this number. This is how much sulfur is needed, how much sulfur I'm starting with in terms of sulfur is I am starting with 0.291 moles of sulfur, which comes from over here. So when I compare these two, I need 0.122 moles of sulfur, and I'm starting with 0.291 moles. What I see is I have enough. That means right there, by comparing those two numbers, that we know that the sulfur in this reaction is the excess reagent, and the iron in this reaction would be our limiting reagent. And we don't need to go any further to prove anything other than our limiting reagent in this case is iron. Again, you could have chose the other reactant. It would give you the same information in terms of which one's the limiting reagent and which one's the excess reagent. Why this calculation here is important is it is always the limiting reagent that tells you how much product you can make. And when you try to figure out how much product, you want to make sure that you start with the starting amount, not any of these numbers like this number or anything like that. So coming back to our starting amount of our limiting reagent, which is 0.122 moles of iron. Again, I'll just put starting there. We are now going to try to figure out how much product we're going to make, which again means we need to go to the equation between our iron, which is our limiting reagent, and our iron 2 sulfide, which is our product. It is a 1 mole of iron gives you 1 mole of iron 2 sulfide. So 1 mole of iron on the bottom, 1 mole of iron 2 sulfide on top, iron 0.2 moles of iron in this case. And at this point, we don't want moles per grams. So at this point, we want moles per grams. Again, we're going to have to delta, and iron is 3, plus is 3. And that tells us that the molar mass of FeS is 87.92 grams per mole. So again, on the per mole, and we will end up with 10.7 grams. Using figures because number 3. Again, now, although this is a limiting reagent problem, you should hopefully be able to see that it really is sort of the same 4 steps. We balanced equation, we converted to moles. The additional step we have to do because it's a limiting reagent, and then we went to the balanced equation, did the mole to mole step using the limiting reagent. And step number 4, converting our moles into grams. So it's really the same 4 steps. You just have to kind of insert that calculation to determine which one is your limiting reagent and which one is your excess reagent. Now, we also could, if we wanted to, in this case, figure out how much of our excess is left over. And we could do that pretty easily because we kind of chose good in this case. We chose from this calculation that we did earlier that if we want to use up all of our limiting reagent, which in this case is the iron, we would need 0.122 moles of sulfur, and we started with 0.29 moles of sulfur. So the leftover sulfur would be our starting amount, 0.291 moles, minus how much we needed, which was 0.122 moles. And that would tell us that when this reaction is over, we would have 0.169 moles of sulfur left over. And we could even use the molar mass to figure out how many grams that would be from the periodic table, 32 grams per mole. And that would get us 5.42 grams of sulfur is left over. So sometimes you might be asked, how much of your excess reagent is left over, and you could kind of do that calculation. So again, if you remember way back over here, this is how much sulfur we started with. We started with about 9.3 grams. In this reaction, we have about 5.4 grams left over. And so we use maybe like 3.8-ish grams of sulfur to do this reaction. So if you don't want to get lost in these calculations, just keep following those same 4 steps. Again, you need to put an additional step if it is a limiting reagent problem. All right, so let's take a look at one more here. So same thing here, we have an equation. We're starting with 622.7 grams of this guy. We're also starting with 1,241 grams of this guy. They were nice enough to give us the molar mass from the periodic table. So the molar mass of NH3 from the periodic table, 1,703 grams per mole. And the molar mass from the periodic table is CO2, adding up all the parts, 4,401 grams per mole. And we want to know how much of this guy will we actually make. I'm just going to roll this back and use the empty space here to do that. So we will start with our same steps. Right here tells us this is a limiting reagent problem because we have the starting amounts of both reactants. We do have a balanced equation. We then want to convert to moles. So taking each of our reactants, using the molar mass, which if it was not provided for you, you would find on the periodic table. And again, same thing with the CO2. If it was not provided for you, periodic table is where you would go get that. And if we convert these guys into moles, we get 3656 for here. And 2820, we'll call it, of CO2 here. Again, just to keep pace, since there's a lot of numbers happening up here, this again is our starting amount of each of our reactants. So just like we've done before, because it is a limiting reagent problem, we want to figure out which one's the limiting reagent. So if I want to use up, I'm just going to pick one. So when I use up all of the NH3, I want to know how much CO2 is needed. So we're going to start with the moles of our NH3. We're going to go to the equation, and from the equation we see for every 2 moles of NH3, which is the coefficient right there, gives us 1 mole of CO2, which is also the coefficient right there. And again, we're going to use that to go from NH3 to CO2. So 2 moles of NH3 gives us 1 mole of CO2. So we're going to divide that 3656 by 2 gets us 1828. Moles of CO2 is needed. So again, this is going to allow us to hopefully figure out which one's the limiting reagent. We need, in this case, 18.28 moles of CO2. We started with, from our beginning CO2, 28.20 moles of CO2. So when we compare these two, we do have enough. So again, that means that the CO2 is our excess reagent, and by default, our NH3 is our limiting reagent. Now, once it's established that this is our limiting reagent, the importance of that is really going to tell us how much product we're going to make. And we want to again do step number 3 here. And we want to use the starting amount of our limiting reagent, which is 3656. And again, this is our starting amount. We are now interested in our limiting reagent, which is NH3, which is 2 moles of NH3, and our product, which is only 1 mole of our NH2 to CO, again from the coefficients. So up on top will go 1 mole of our product. The bottom will go 2 moles of our NH3, which is our limiting reagent. And we'll take 3656 divided by 2, gets us 1828 moles of our product. And again, we want grams, so we need the molar mass of our product, which we could get from the periodic table. I think it was actually given to us in this problem. I just personally don't remember what it was, so let me just calculate real quick. 2 times 1401 plus 4 times 1.008 plus a 1201 plus a 6006, it looks like. So if you go to periodic table, 6006 grams per mole if you add up all the parts. And we will use that, the 6006 grams per mole of our product. The moles will cancel, and that will get us 6006 times 1828, about 1,098 grams of our product would be produced. And this again would be our theoretical yield. So again, same 4 steps. 1, 2, 3, and 4. Additional calculation needed because it is a limiting reagent problem. Now, the last part of the question was also, just like we asked before, how much of that excess reagent is left over? So we will squeeze it in here to determine how much is left over. Now, we could do that right here. Since the CO2 was our excess reagent, we know that the leftover of our excess, which was our CO2, we know that we started with 28.2 moles of it. We needed 18.28 moles to do this reaction, which was right here what we calculated. And if we subtract that, gets us 9.92 moles of our CO2, which then if we take 9.92 moles of CO2, we times it by the molar mass of CO2 from the periodic table, 4401 grams per mole. That will tell us that we have about 436.6 grams left over. 436.6 grams of CO2. That again is, I'll just put leftover, yeah. And again, we started with about 1,200 grams of CO2. So in this reaction, we used about 700 grams or so in this reaction. Again, hopefully you should start seeing a pattern as to how to do these problems. Really the same 4 basic steps. Even if it's a limiting reagent, we just need to do that additional calculation to figure out which one's the limiting reagent. And then obviously, just like in all calculations when you're figuring out products, always the limiting reagent you want to use. All right, here. We'll scroll that through. So that brings us to yields of reactions. And there's a couple different types of yields that we come across. Some we've already come across. And the first one is the theoretical yield. And as we've seen in all these calculations we did so far today, the theoretical yield is your maximum amount of yield. That is the one that you actually calculate from the equation. So when you calculate how much product you're going to make based on how much you start with, the limiting reagent, and the product that you make, that is your theoretical yield. That again, as we've been talking about, is your maximum yield. That's like everything went 100% perfect. Nothing fell, nothing dropped, no side reactions. Based on the equation, how much you start with, that is how much you should produce. Life isn't like that. So we have another yield, which is known as the actual yield. And the actual yield is, much like it sounds, actually how much you actually made when you did the reaction. Reactions don't work out 100% all the time. So you do get this actual yield, which is usually smaller than your theoretical yield. Sometimes your actual yield can be larger than your theoretical yield, but those are usually not good situations. Those are situations where you messed up, basically. So you had too much actual yield. So usually your actual yield should be less than your theoretical yield. And what we do with these is we put them together and we calculate oftentimes what is known as the percent yield, which is the actual yield, which in most problems are given to you in the problem. The theoretical yield is usually what you have to calculate, and you divide it times it by 100, gives you your percent yield. Closer to 100%, really good. You did the experiment great. You know, in your high 90s, that's really good. You got like a 5% yield, you probably dropped some stuff along the way. You didn't do so well. So usually a higher percent yield is what you're looking for. Usually you don't usually get to 100. Somewhere in the high 90s is usually really good. If you get over 100 again, that usually means something probably didn't go so right. So let's see how this works using sort of the same reaction that we just saw. So in this case, we're going to take 100 grams of each of these. And we are going to produce 120 grams of this guy. And we want to know the percent yield, which is our actual divided by our theoretical times 100%. So when we see this number, this is actually what we produced when we did it. So this is our actual yield, which is typically given to you in the problem. So that means in order to calculate the percent yield, we do need to calculate the theoretical. So that is going to involve a calculation. Now, we're going to do it the same way as we did before. We're given the starting amounts of both reactants, which will tell us that it is a limiting reagent problem. So just like we did before, we need to figure out the limiting reagent. So same steps, we're going to balance the equations, the same one we used previously. We're going to convert to moles. Here we're using different numbers. So grams of NH3. We're going to use the molar mass from the periodic table of NH3, which I hope from the top of my head is 1703. We're also going to do grams of CO2, which is 4401 from the periodic table. Again, these are the same numbers that we used previously. And we will get 5.872 moles of NH3. And we're dividing by the 4401 gives us 2.272 moles of our CO2. So again, just like we've done previously, this represents our starting amount of each of those. So we'll put starting up here. So because it is a limiting reagent problem, we need to do that little calculation to figure out which one's the limiting. So here I'm going to try to use up all of my NH3. I want to know how much CO2 is needed. So we're going to start with our NH3, our 5.872 moles of NH3. We're going to go to the equation and find the relationship, which is the same one as we used in the previous problem. 2 moles of NH3 gives us 1 mole of CO2. And if we divide that number by 2 there, 2936 of CO2 is needed. So again, at this point, we want to compare how much CO2 we started with to how much we needed. So we started with, in this case, of CO2, 2.272 moles. We needed, based off of our calculation, 2.936 moles. So when we compare how much we need to how much we're starting with, we see we actually do not have enough in this case. So in this case, based on what we're starting with, the CO2 here is the limiting reagent. The NH3 is the excess reagent. So that's why that calculation is really important, because it will tell you which one is which. Now, once we determine that, that is going to allow us to continue on to step number 3. Again, we want to use our limiting reagent, the starting amount, to do this calculation, 2.272 moles of CO2. And again, that's our starting amount of our limiting reagent. Now we can actually figure out how much product. And again, it's the same relationship. So our limiting reagent, which is our CO2, is 1, and our product is 1 in this case. So 1 mole of CO2 from the equation gives us 1 mole of our product. And I could do that math, I think, 2.272 moles of our product at this point. This would be our theoretical yield in moles. But since our actual yield's in grams, we probably want to continue on and do step number 4, which is use the molar mass. And again, we could use the same numbers we used in the previous example, because it's the same thing. And I believe that number was, let's say, 60-ish. 6006 looks right. So again, if you didn't have it, you would go to the periodic table to get that. And if I take 6006 times what I got there, 2.272 times 6006 gets us 136.5, looks like. 136.5 grams of our product. And this is our theoretical yield in grams. So this number is the bottom part to what we need. So to calculate our percent yield, we're going to take our actual, which was given to us, divided by the theoretical, which we just calculated, times 100%. So actual was 120 grams. Our theoretical was 136.5. We're going to times it by 100. This is why we want the units to be the same when we do it. And that way they cancel out correctly. And that gives us 87.94% yield. Not too bad, not the greatest. Would be our percent yield. Now, when you do calculate percent yield, your actual and your theoretical times 100%. The units can really be anything as long as they're the same. So you could technically do moles divided by moles times 100. Or like we just did there, grams over grams times 100. But they do have to be the same unit on top and bottom in order for everything to cancel out correctly. So a percent yield problem is really just a stoichiometry problem where at the end, you stick it into here and you calculate your percent yield. And I believe that should be it. So to summarize what we talked about here today, we finished up talking about stoichiometry in chapter 5. This should complete chapter 5. So there's a lot going on in chapter 5. So make sure that you watch these videos again if you need some help or kind of go through it. But you do need to be able to do basic stoichiometry problems, which does not involve limiting reagents. You need to be able to do limiting reagent problems, which involve when you have two reactants given to you. And obviously, you need to be able to calculate the percent yield. This should hopefully conclude our recorded lecture series here on chapter 5. Thank you very much for listening. And again, these will all be on Canvas if you need to go back and watch them again. Other than that, have a good one, and I will see you next week, I think.